So thank you very much for having me here at Google. Today's Tech Talk is called Learning from Code History. And I guess I should start by telling you a bit about myself. So starting a bit with code history, or maybe a bit of history itself. More precisely, let's go to the year 1997. Anyone here being conscious already in the year 1997? You look so very young to me, you know, it's okay. I'll give you a couple of hints. What was all the rage in '97? We had the movie Titanic. There was The Lost World, and there was Protecting the Earth from the Scum of the Universe. Could have been early Google logo, I guess, that one. There also was, in terms of songs, there was, for instance, Elton John, like Candle in the Wind, Princess Di had just died this very year. There would be Los Macarenas, with Los del Rio with Macarena, the Spice Girls all together, If You Want to Be My Lover and all that, and Chumbawamba for those of you with a more socialist touch. And and finally, that was me in '97. Actually, I don't belong really in this group, because in 1997, I was doing my PhD thesis, and then PhD thesis was called Configuration Management with Version Sets. You think, oh wow, that's configuration management. It has something to do with code history. But actually, that's not so much the case. I was at a chair where formality and coming up with cool formalisms was all the rage, and applicability only came at a very distant, only at a very distant pace. We would bash our heads against each other on finding good applications for linear logic. So first came the formalism, and then came possible applications. And my PhD thesis is somewhat along this direction. It uses description logic for modeling version control, modeling version histories. After I finished my PhD thesis on version control, I thought I wanted to do something rather useful for a change. So instead of looking at code history, I actually looked at code. And a student of mine, Dorothea Lütkehaus, and myself, we came up with a debugger, with a visual debugger called DDD. The fun part about DDD is its ability to visualize data structures. As you can see up here, there's a linked list, as you can directly visualize it within DDD. That was a pretty fun tool. DDD was postcardware. If you liked it, you could send me a postcard, and eventually I got a whole bag of them. And while we were working on DDD and making release after release, well, we encountered the usual problems of maintaining a program that's being used by hundreds of developers all around. Well, hundreds. Well, would rather be tens of thousands of developers all around the world. And of course, we would also get bug reports like this one, for instance. This came from a guy at Motorola, and he described that his earlier version of DDD had worked, but now DDD was a front end to command line debuggers called GDB. And he had upgraded the GDB component, and all of a sudden, DDD didn't work anymore properly. This was a classical situation. You have something, say, your old version of the operating system, and now you install the new one, and all of a sudden, things break. Well, and that's when, even though I had a debugger at hand, I would have to enter the usual mode of debugging, which would be at the time, well, sitting in front of your laptop, of your computer. You look at the code, you have a piece of, well, caffeine drink, or maybe have a smoke if you're so inclined, and it gets late, you realize you're still hungry, you're getting your pizza, and you're back to your computer, and having another drink, and look at the code again, and have a smoke. Maybe in between, your significant other calls you up, and most likely at the moment when you're really, really when you're totally concentrated, when you're in the flow, and you're getting this call, where are you right now? Come on, please come home at this point. And you realize that while you're talking, you're starting to lose it. You're losing your concentration, and you have to cut short this call because either because you're losing your concentration. It will take you another hour to get back into that mode, and you have to cut short your significant other, which is an awfully bad thing to do. The other choice is to lose your code, which is also an awfully bad thing to do. And this is how eventually, well, you spend your days and nights with debugging. And actually, I wouldn't be surprised if half of the divorces in IT actually have some background in staying late for debugging or staying overnight for debugging. Maybe it's even, say, if you have a significant other and you cheat on them, that's one thing. If you cheat on them with a computer, that's really, really bad. And also, while maintaining DDD, I had to debug like crazy, and like almost everybody else, I never got any formal training in debugging, and I didn't know how to do that. Well, and I did my best in doing it. So I wondered, and at this point I wondered, say I had done this work on version control, I wondered whether there would be a way on leveraging the history of changes, leveraging the code history in order to debug better, in order to actually solve problems. And the first thing I came up with was actually using code history to simplify problems. So let's come back. So what do I mean by that? Let's come back to this bug report. This is we have this situation. I have an old version that worked and a new version which no longer works. And in this case, the appropriate engineer had upgraded GDB from an old version to a new version, and lo and behold, there we go, our things just broke. How do you figure out what precisely caused the problem to occur? The first thing I came up with, and that's pretty straightforward, is called bisection. The idea is pretty simple. Again, here's an arrow of time, and you have a situation yesterday where your configuration worked, and you have a today's version, which no longer works. Between these 2 points in time, something must have gone wrong. Straightforward. So what you do is, for instance, you look at a place, say, today morning, check it out, does it work or not? Well, it worked, so maybe it's today afternoon. Lo and behold, today afternoon, it no longer works, so something must have happened between today morning and today afternoon. And by doing this sort of binary search, you can continue this for a number of times. You eventually figure out, hey, here's one precise point in time where some change was made that made the program go wrong. I actually did precisely that. And in the case of GDB, I immediately found that there was one single point in time where, unfortunately, not only one change had been applied. Well, actually, there was one single logical change, and this one single change that had been applied was 178,000. So the diff was 178,200 lines long. That's pretty amazing if you consider that GDB at the time had about 500,000 lines. So some of these changes actually came from a change of address of the GNU Foundation. So every single source file was changed, but there were also plenty of code changes in there. And so my wonderful scheme of figuring out what had changed didn't really work. It turned out that what I was actually looking for is a causality problem. Causality problem means that you have two situations. You have one world in which your problem occurs, or in which the effect occurs. This is when the program fails. And another world where the program works, where the effect is not there. And actually, if you look at the definition of causality, in particular the counterfactual definition of causality, you will find that the cause is precisely the difference between a situation in which the effect occurs and in which it does not occur. In our case, we had the unfortunate situation that the cause was there. Upgrading to GDB made the program fail. There it is. Here's your cause. You didn't know that beforehand. You can even come up with other causes. You can also say that, for instance, oxygen is the cause for my program to fail. Because without oxygen, which would be an alternate world, there would be no developers, and without developers, there would be no program, and therefore there would be no failing program either. There would also be nobody to witness it, and so we could immediately stop it. So this idea of causality as a difference between worlds is not necessarily something that's useful. But fortunately, this problem was also discovered by David Lewis, who was a philosopher in England at the time. And he said that, well, there's actually a better definition for causality, because what he introduced was the concept of actual causes An actual cause is not an arbitrary difference, but it's actually a minimal difference between a situation where the effect occurs and where the effect does not occur. In our case, this would be the difference between a program working and a program failing, and we want to have a difference that's as small as possible in order to figure out what the cause is. So, how can we apply this how can we apply such a definition in order to figure out what the problem cause is? Well, you can again go and systematically try to narrow down these differences, more precisely narrowing down the difference between a situation today where the failure occurs and a situation yesterday where no changes have been applied. So if something is bright up here, this means a change has been applied. If something is dark, change has not been applied. Now we have a multitude of changes, and something in between here has gone wrong. So how can you do that? Again, you can do a binary search, for instance, by applying half of the changes. And this is actually something I did. What happens if you apply half of the changes? Well, you test it. And if you figure out that, for instance, the program now works, then what happens is you now know that the failure cause must be somewhere within that difference. That is, this difference here, no, there's no difference anymore, so you have just narrowed down the difference by 50%. You can do this again in sort of a binary search, again narrowing down the difference. If you find that there's a failure up here, you again have narrowed down the difference to another half. And you can try this out again, but the bad thing is that this may not work forever. For instance, what happens if you have an undetermined test outcome, which is actually likely if you take just a subset of the changes, apply them, and want something meaningful to come out of that? Well, this doesn't help you any further. Same thing goes if you take the other half. Let's assume for the other half, we also have an undefined test outcome. This doesn't help us, so we're stuck in here. There's no way we can continue with just binary search in here. So the idea that I came up with, and this is probably the one single idea that was most significant in here, is maybe we can come up with something that's not right halfway between these two configurations, but rather something that's closer to, in this case, the failing run. That is, we only apply a smaller set of, we apply a larger set of differences such that the potential difference is smaller. And it turns out that if you do this repeatedly, you eventually come up with a configuration where you have a determined test outcome. That is an outcome where for instance, in here where the program fails. You can continue this game, narrowing down the difference again and again, systematically, until you do have just a minor difference in here, a minimal difference in here, which remains. In this minimal difference between these two configurations is the failure cause. Now, let me repeat this again. The idea is you have an automated test which tells you whether a configuration is failing or passing, or whether it yields an an unresolved result. And then you have a strategy that systematically narrows down the difference between a passing and a failing run until it has narrowed down that difference to a minimal difference. And this minimal difference then is indeed an actual failure cause. There's also formalism behind that. You can actually formalize this pretty well. You have a testing function which returns you either a pass or fail or unresolved. And based on these definitions, you can actually describe the entire strategy for narrowing down these configurations in 7 lines. Well, let's make that 8 lines of things. If you're from France, for instance, if you're interested in formal methods, this is your slide. Please have a look at it. It actually took me quite some time until the entire algorithm would fit on one slide. So actually, I was applying the simplification process to the algorithm itself. And this algorithm later became known as delta debugging, because delta debugging, the idea is to have a delta between the passing and a failing situation, and you narrow down this very delta until you find a failure cause. So this was for the formal people. If you're more programming inclined, here's the very same thing in Python code. Actually, I was programming in Python at the time, so I still have it in Python. If it were, also Python had the big advantage of the entire algorithm fitting on one slide again. If I had done this in C++, I would have, would have used 2 slides. So the entire algorithm, this entire delta debugging thing, actually fits on one single slide. All you need is a testing function that takes care of setting up the appropriate configuration and coming up with an appropriate outcome. So this is what delta debugging does. And so let's come back to our original GDB situation. I have actually applied delta debugging to GDB, and this is the log of the actual run. Actually, it's under multiple configurations. What you found in here is, what you see in here is this line going down here, and this line, the y-axis tells you how large the difference was. Initially, we still had 8,720 changes in here. You see this is a logarithmic scale, so don't worry too much about it. And you see that for some time, it stalls around 2,000 changes where it's not able to find a combination that comes up with a resolved test outcome. And then all of a sudden, we have a large drop down here after approximately 60 tests. We have a large drop down. That's precisely the situation when all of a sudden half of the changes already suffice in order to make the failure occur again. And then it rapidly goes down and down again until finally, after 98 tests, that's 1 hour. That's 1 hour on a regular PC. If you have a multi-core machine, say 16 cores, you can easily divide this by 16 because it's very easily parallelizable. So after 1 hour, what you get in here is the actual failure cause. The failure cause is just one line that was changed. And lo and behold, it's not even code that was changed. It's not even code that was changed, but it's a documentation string. It's a documentation string within GDB. And this is because this is actually if anyone ever used GDB on a raw command line mode? Oh yeah, I see people nodding. Yeah, that's a pain, I know. But it's very powerful at the same time. If you type something like help set args, this is the text that you get. This is the documentation for the set args command. Or in the old version, it was set arguments. In the new version, it was set argument list. This is the text you get when you type help set args. At the same time, though, this very help text also is the base for the output of the set command. Through some pretty magical thing, if you type view args, then this very prefix of this help text is being used in order to print out the argument list. It probably saves 24 bytes or something like that in the executable. And of course, if you were born in the 70s or 60s, this is really something you should get. That's a huge difference. And so this documentation eventually became the output. And this output of argument could probably be parsed by DDD, because DDD expected a string to start with arguments, and GDB put out the wrong output in here. So, okay, I saw the difference. I knew what it was. So I patched DDD in order to come up to accept anything that would start with arg. And then, as far as I understand, until today, it's still working properly. So I wrote a paper about this, and I called this, yesterday my program worked, today does not why. My advisor didn't like the title at all. My co-advisor for my PhD thesis didn't like the approach at all. When I gave the talk at the conference, people were actually asking me. So he came up with something so simple that's really amazing. I mean, why did you get your paper accepted for that? And I said, well, it took me 1 year to get it that simple. Oh, we wouldn't have believed that. Okay. Well, actually, I draw quite some criticism on me. But incidentally, just this very September, this very paper got an award for being the most influential paper of 1999 when it was published. So in the past 10 years, well, not for the entire period of the past 10 years, but at least in software engineering, that was one of the more influential papers. We also wrote a tool called DD Change, which would implement this for the Eclipse framework. Initially, we pitched that as debugging at the touch of a button. So you just press one button, and delta debugging would automatically figure out what the change was. It draws on the local history as well as on the global history of a system. And my student eventually also figured out that not only with delta debugging would you be able to figure out what the cause was, you would also be able to immediately automatically fix it. Because all you need to do is to revert that very change. Delta debug, if you apply delta debugging, you can actually prove that the failure at hand will be fixed. That's within the algorithm. Not sure though whether this would introduce any other problems. So actually, I asked him to have a dialogue that would confirm this whole thing. He always wanted to go entirely without dialogue, and in terms of simplicity, I think that going without any dialogue would have been even nicer. So while you're programming and you make a mistake, delta debugging steps in, finds out what the change was, reverts the change, and maybe it can put some squiggly lines under the code that it just reverted or something like that. There's many ways to put this into a nice user interface. Our delta debugging even made it into the Wikipedia, and in the Wikipedia you can also see that there's a number of additional uses for delta debugging. For instance, if you have a program input, you can use the very same algorithm to figure out what part of the input made your program go wrong. Suppose you have this big SQL query, for instance, and you send this to a database crashes. You want to figure out what's the part of the SQL query which makes my database crash. You have a big HTML input, you'd send it, say, to Internet Explorer crashes, and you want to figure out what was the part that made it crash. You can also combine this with random testing. You create a big input randomly, send it to some program, it shows a failure. You want to figure out what it was, you can use delta debugging for that. You can also use that for user interaction. That's the fun part. We had an experiment with Mozilla at the time where we had a description of 7 steps that you needed to select specific menu items and press specific buttons in order to make a printing failure occur. Turned out that only 3 keystrokes sufficed. That is hitting Control, hitting P, and release P again. That was all it took in order to make the browser crash. And of course, changes to the program code as we just seen it. I should add, though, that there's this nasty node right now within Wikipedia. So in case you have nothing else to do, feel free to add more material to that article. Okay, so that was learning from code history a bit on how to simplify problems. And as I thought more and more about this, debugging problem, and thought about okay, these are ways to debug things automatically. Well, I guess I made the obvious next step, which everybody who's been debugging too much thinks about. The question is, so debugging is a good thing, and if we can automate this, that's also a good thing, but how about not having these bugs in the first place? And so I went into thinking about whether there would be a way to prevent such debugging problems. And again, I was thinking about leveraging code history for this very purpose. The idea is as follows. Here's Bugzilla, a bug database. You have a problem with, say, Firefox. You enter this into the bug database. Hundreds of thousands of entries in here. Whenever somebody reports a bug in Bugzilla, this goes into the bug database. And after it's been to the bug database, well, there's people like you folks who look at the bug database, eventually fix it, and therefore commit a change to the version database. These 2 databases are frequently separate. Bugs would be handled, say, in a system like Bugzilla. Versions would be CVS or Subversion or some other version management system, although you can just as well merge the 2 and have an integrated system. The idea now, though, is that we wanted to know where would bugs occur in our system. Where would bugs be fixed in our system? So we came up with the idea, how about we look at the individual bugs, figure out where they have been fixed, and then figure out, well, are there places where bugs tend to accumulate? This is one of the earliest studies we made. This is for the SPECJ compiler. Maybe some of you have been programming in SPECJ. Let me tell you that the SPECJ compiler is a super tool for doing empirical studies like that because it has plenty of opportunities for improvement inside. We always use it for our studies. I've seen code in there which just made me laugh and scream at the same time. It's in development, and what you see in this picture is every rectangle stands for a class, and the color of the rectangle tells you how many bugs have been fixed in that particular class, and the size of the rectangle tells you how large the class is in terms of lines of code. So what you see in here, for instance, this is a place where 16 bugs have been fixed over time. The dark places in here mean that there have been no fixes in the past, and it goes up to, I think, there's places in here which deal specifically with aspects which go up to 25 bugs which have occurred in this particular place. I should add at this point, the fact that no bugs have been fixed in these dark places does not necessarily mean there are no bugs. So we're not counting the number of bugs there are. We only count the number of bugs that have been fixed. If I wanted to start the number of bugs that I could find in SPECJ, I could probably, if you spend me $1 for everything I consider a bug in SPECJ, I could probably make a nice living out of that. No, these are just the fixes. So, but still, you see that these fixes that there's places where there's many, many more fixes than others. And so we wondered, how can that be? We also did a study on Firefox. Firefox, well, it's almost a Google product. Well, oh no, that would be Chrome, of course. But Firefox is in Google. Well, there's a certain relationship in here. And in here, in this Firefox study, we only looked at a specific class of bugs, namely security violations. So we wanted to know whether there would be particular places within Firefox where these vulnerabilities accumulate. And again, the redder a rectangle in here, the more security bugs have been fixed in this place. What you see here in the left lower corner, this is actually JavaScript. You see here, there's the JS source, and you see JavaScript obviously is a good playground for security vulnerabilities. Plenty of security vulnerabilities have been fixed, but there's also places here like there's the base, there's a class in the HTML layout which has been fixed again and again, and other places over here there's the document object model which is over here. These are places where security vulnerabilities have been found and fixed, for instance, because of cross-site scripting. And the idea, of course, is such a map is something we can generate more or less at the touch of a button, because all we need to do is we map the individual bugs, the individual changes, the fixes, and then we know for every single fix where it has occurred, and so we can assign it to a particular component in here. And then, of course, once you have such a map, you know where to focus upon. You know where to focus your tests upon, and you know where the bugs are. And if you're looking for security vulnerabilities, well, these are the places you should start with. What we also looked at is, since we were scientists, wanted to know, where do these bugs actually come from? Is there a correlation between the number of bugs and any other feature we could find? And this was a very fun game to start with. First thing we looked at, is it the developers? Sure, developers make bugs. That's where bugs come from. But does it make a difference how experienced you are? In the first study of that kind, we did that on Eclipse and on the Eclipse bugs. Number two on the list of developers who made the most bugs was Eric Gamma himself, the head of Eclipse. Number 3 was Andre Weinand, who's another head developer. It turned out that the more experienced the folks were, the more bugs they made. Before you now go out and bash your manager, Let me tell you that I actually I talked to Eric Gamma about that. We sent these results to him, and we talked about that. We were having a joint plane flight, and we had lots of fun. And so I asked him, how Eric, come on, you're one of the smartest software architects around. How come your code is so bug-ridden? Oh, that's very easy, he said, because you know, the developer there's always problems that developers do not want to tackle. So here's developer A, and here's some piece of code which is too risky. So he escalates that to his supervisor, who again escalates that to his supervisor, who then escalates this to me. And I have nothing to escalate it to, so I have to do it. So he's the one who has to do the most risky things, because he's the most experienced. And, well, because he does all the risky things, well, he also makes the most mistakes. See, if you start as a, well, I guess that's at Google is pretty much the same. On the very first day of your work, you don't start to work on the crown jewels. You get some assignment which is less risky than that. And this is the reason why we found that the more experienced people were, the more bugs they made. We also looked at history. If you found lots of bugs in one place, will there be more? The answer is yes. It's like fishing. You go fishing in one place, find some fish, come back the next day, yep, there's more fish. Fish tend to accumulate in specific places where they like it. Same for bugs, except that for fish, we do have a decent theory on how they reproduce. For bugs, no such theory. We looked at code metrics just to have fun. You know, there's a big branch in software engineering, considering big branch that takes care of complexity metrics and all that. Do complexity metrics correlate with bug density? We looked at that, and the answer to code metrics is sometimes. Sometimes they correlate, sometimes they don't, which is, from a scientific standpoint, more or less worthless. Oh, and we found that not only on a number of open source systems, but also on Microsoft code, for instance, including Internet Explorer and parts of the Windows kernel. Yeah, sometimes they do, but there's no pattern in there which would help you in any way. Something else, testing people in here will also look at coverage. Is it so that if you test some piece of software a lot, that there will be less bugs in there? Actually, it's the other way around. The more you test something, the more bugs will be in there. This may be surprising. This may be surprising at first, but there's a reason for that. There's a reason for that. So you're a test manager, and you need to decide, where do I test? Okay? And of course, you test in the places where you suppose the most bugs. You know, here's a place which is probably bug-ridden, so I'm going to throw one more test and another test and another test at it, and you increase the coverage. But yes, your intuition was right. Your tests are still not enough, though. So yes, test coverage very well correlates with bug density. Testers are actually pretty smart people, except that, well, except that the tools for squashing the bugs are not smart enough. And we also looked at language features because that was fun. You know, well, if you were born before 1970, you probably remember this famous quote by Dijkstra, or this famous paper by Dijkstra: "Goto is considered harmful." If you were born afterwards, you never saw Goto in your life, probably because of that very quote. Actually, we actually looked for Gotos, more precisely the equivalent of a Goto. That would be a break with a label in Eclipse code, and we figured out, well, if there's a Goto, there should be some correlation with bug density. No correlation at all. If anything, code with Goto tends to have a little less bugs than regular code, simply because code with Gotos has a higher likelihood of being generated code rather than written code. While we were at it, we actually had a look at all the tokens there were in Java at this stage, whether there would be correlation with anything. Some people say that do-while loops, for instance, are more bug-prone than others. It turns out that there were 3 tokens: import, extends, and implement. Yep, you know these are the tokens. These are the language constructs that determine which other components your component interacts with. Interestingly enough, though, it wouldn't be the number of such tokens. So it wouldn't be the number of imports, but more precisely, it would be what you import. What you import, what you extend, and the interface you implement, this would determine how many bugs there would be in your code. This was a fun. So for instance, in Eclipse, if you go and import something that starts with org Eclipse compiler internals, you're pretty much doomed, because your chances of having a bug is about 7 times higher as if you import, say, something like org Eclipse GUI something. That's why newcomers would rather work on GUI rather than compiler internals. Compiler internals is the stuff that every gamma has to do. See, this is how it all fits together. The nice thing, though, is that what we found is that you could actually use these imports pretty well for predicting whether your component was going to have a bug or not. In Firefox, for instance, if you included in C++ these two header files, ns private DOM event.h and ns readable utils.h, you're pretty much doomed. Because these are all the 20 source files which include these two header files, and all 20 of them had a security violation. And no, it was not the same security violation all over, but actually it was a number of different security violations. So for some reason, interacting with the document object model is just super risky. Well, again, all these bugs are also fixed. If I talk about the number of bugs, I always actually mean the number of fixes I've seen so far. We actually used this for making a prediction. So we trained a machine. We took a machine learner and we trained it on 2/3 of the code in order to predict for the remaining third of the code, based on their imports alone, based on their include files alone, whether these would be risky or not. And this is our ranking as we predicted it at the time. And this is the prediction. NSDOM class info would be would be the one that would have, in our prediction, the highest likelihood of having a security violation. And then you can just go down the list. And if you look at the actual fact in here, this is the real number of security violations in here. You can see that we were actually pretty good, because 1, 2, 3, we actually found 6 of the 10 components with the most security fixes in there. So our prediction was pretty accurate. What was even more impressive was that half a year later, when we revised our work, turned out that 2 more files in the meantime have had a security violation. So we were pretty happy. Not only did we have a simulated prediction, but we actually had a real prediction. So these files, which at the time weren't known to have a security violation, were actually properly predicted by us. So this is also something your version history can give you. It can tell you where the bugs are. We're able to calibrate a bug prediction based on appropriate features. We can predict where the next bugs will be. And again, this is an automatic technique. You press a button, you get the map, you can get the prediction. All of this is part of a movement which we helped to build. That is mining software archives that contain a full record of the history, that are maintained within programming environments. You don't have to do any extra effort as developers in order to take care of them, because, well, version history gives you enough benefits for that. All the maintenance and access is fully automatic, and for research purposes, for us in particular, there's plenty of such open source archives available. And besides bugs and versions, well, there's much more. There's the code to look at. All the static analysis techniques you can think of are in there. There's models to look at. There's specifications, formal and informal specifications. There's email between developers which you can leverage. There's effort data in order to predict where the effort will be. There's traces around which come from which can either be collected in the lab or from actual users, that is profiles. There's chats between developers. There's test data available on how the individual parts were tested and when and what the results of this was. And there's also even people who collect the navigation data. That is, they collect where developers, what the piece of code is that developers actually look at in order to make prediction which parts of the code are related to each other. And the big challenge is for us as researchers to bring all these individual sources together and to make use of them. This is actually a pretty neat situation because in the past, in order to get such data about real developers and real development, the process was much more painful. Just recently I asked an empirical, well, recently, that's 2 years ago, I asked an empirical researcher what his most important tool would be in order to collect data about the development process. He says his most important tool is the phone book. Oh, a phone book. So do we actually look for, say, hierarchies of people or joint telephone numbers in the phone book? No. I use the phone book and I call up the developers individually. So I make a phone call and say, dear Herr Leitner, hello. You've been in charge of testing this YouTube component. Can you tell us, this was about 3 months ago. Do you still remember what the results of this test were? Did it fail? Then Herr Leitner will hopefully remember and say, yes, it sometimes failed. Thank you very much. And you have another data point. This is how lots of empirical software engineering is done, and is still being done today. And at the end of this huge effort, not only from your side, also from the developer side, because you actually interrupt them in your work and torture them with appropriate surveys, at the end of the day, you get a glass of water, a glass of data. You get this glass of data, you drink it, you're done. What we get with looking in these archives of changes, of version histories, this is not you have to go to the data. This is the data that comes to you. And there's much more than it, much more in it, and much more than we as researchers could ever think of processing. What do we do with such development data? It's fun. So we can do studies. Say, 3 years afterwards, we show, here's a curve that tells you how much effort goes into individual stages of development. Sure. We can also go and make nice visualizations of it. But the thing that I like most, actually, is to make this data actionable, to have consequences that follow. Something like that tool, for instance, a tool that tells you during your software development where you are, where you should go, how much time it's going to take you. If you choose to take another path, if you choose to take another path, it will happily take this into account, and constantly taking care of you, looking over your shoulder, and leveraging the experience of the entire development so far, as, among others, it becomes manifest in the history of your code. So, if you want to learn more about these, here's a couple of references. This is the book Why Programs Fail, which Andreas mentioned initially. This is lots of material from the systematic debugging side, both automatic debugging techniques, but also how to improve your manual debugging, and coming up with many more techniques than the one I just showed you. There's a book on software evolution, which actually describes our research into mining these databases, open source databases in Microsoft. If you're interested, there's one chapter of the book that is freely available on the web, and incidentally, it's ours, so you can read the chapter without buying the book. There's also the book Beautiful Code, which I understand is pretty popular around here. There's a chapter by me on delta debugging, which describes how the whole thing works, including code, the appropriate code snippets. And while I'm talking about Beautiful Code, there's a new book coming out, Beautiful Testing, which will be out in the first copies have been sent to the authors a couple of weeks ago. And this book, Beautiful Testing, also has a chapter from me and my co-author where we describe something that's not related to leveraging version history at all, but where we describe our latest and greatest in efforts, our latest and greatest achievements in terms of testing in particular. If any one of you has ever heard about mutation testing, we're the first ones in the world to scale up mutation testing to work with programs of 100,000 lines of code and more, and this is also in this beautiful testing book. Okay, with that, learning from code history, I've shown you 2 topics on how you can leverage code history. First is for simplifying problems, techniques like delta debugging, who dive into the history of your code in order to figure out what the problem cause is, and preventing problems, that is trying to figure out in the code history what went wrong, where did it go wrong, and therefore focusing on specific parts of your code. Here again, delta debugging, giving you the failure cause, and finally mapping these bugs to individual parts of your program. And here again, reference for further books. That's for today. Thank you very much for your attention. And I'm happy to take questions. So please.
Gaurav here has a question. Can you hear us?
Yep. So the question is, we discovered that using specific APIs, interacting with specific modules, increased your chances of having a mistake. And the question is whether there would be a metric for that. I've been thinking about that for a long time, but I have not been able to come up with a good metric on that. Why is it that a compiler is harder to program than graphical user interfaces? Well, actually, user interfaces are tricky in their own right, but this is more of an aesthetic or more of an ergonomic problem than if you deal with a compiler. In particular, there's one thing that strikes me. If you do something wrong in a compiler, chances are that the bug is going to stay hidden, and is going to stay hidden for a long time until after release. Whereas if you do something wrong in a user interface, it's going to jump at you the very moment you start the program. And but coming up with a metric that captures this violation of hidden assumptions, as I might like to name it, okay, is very difficult because, well, you cannot simply measure how hidden an assumption is, or the assumption is hidden, it's not there, you cannot qualify it. And coming up with a way of figuring out that there actually are a number of hidden assumptions, number of hard hidden constraints, that's quite a research challenge. That's number one. Number two actually is that, and this is worse, the number of bugs that escape into production is actually pretty low. So all of these are pretty isolated incidents. It's like if you try to establish a pattern from plane crashes. There's not that many plane crashes anymore, okay, than there were in the past. So every single plane crash today comes to be because of a chain of individual, very unlikely events, and each of these events is unlikely, has been taken care of, and it's simply bad that these events all happen to take place at the same time. But it's very hard to establish something like a pattern that this is occurring frequently, and we're running into the same situation with software these days. Bugs are hard to predict. That's good. That's a bad thing. But at least we know where they have been fixed, and we can therefore make a prediction on where the next bugs might be.
I have a question. Can you hear me?
Okay, please go ahead.
How do we verify that the failure cause found out by the algorithm is actually the failure cause and not just a deviation?
How do we know? How do we know that the cause that we find is actually a failure cause and not just a random deviation? That's what you say? Okay.
Yeah.
Well, this is a tricky question because in order to actually you want two things. You want a cause because you know this is a cause, and if I remove it, the failure will no longer happen. And the second thing is you also want an error. This is plain wrong and therefore needs to be corrected. What you want in debugging is something that's both a cause and an error. A cause is something that can be verified. A cause is something that can be verified experimentally. This is what delta debugging relies on. But figuring out that this particular place in your code is something that is wrong is something that's almost impossible to decide automatically, just because, as you know from your daily work, it's very easy for multiple developers to totally disagree on where and how a bug should be fixed. And there simply are many ways typically to fix a program, to fix a program and to evolve the program, because fixing a program in the end is writing a program. And there are many ways to write programs. So I would be happy if a system could tell me this is not only a cause, but this is also plain wrong. But in order to tell that this code is plain wrong, the system needs to have an idea of what the right code should be. And I'm not talking about the specification that the output should be correct. No, this line of code is wrong because. And this is something that can only be done if you have extremely fine-grained specifications that tell you whether every single line of code is right or wrong. If you do have a specification like that, you can just as well use it, and you can just as well use the specification instead of your code, because then you also know the correct code. So this is a limitation of these tools. They can tell you the cause, and in the case of changes, they give you a very good hint. This is the reason why the thing failed. But this doesn't necessarily mean that reverting that change is the best way to evolve your program. It just gives you a good understanding. But then again, it's up to you and your authority to evolve the program again. So the human stays in the loop. That's a good thing. Did I ever study programs that are unusually bug-free? Like for instance, email transfer programs or like things are, of course, the programs we looked at had very large differences in terms of bug density. There's programs with very few bugs. There's programs with lots of bugs that are being distributed, and yes, we see these differences. But again, it's from a number of say 20 projects that we investigated. It would be hard to tell. Here's a specific feature in the development process that's much better in terms of preventing bugs than another one. Ah, yes. Yes, yes. Colleagues of mine also have looked into pairs of programs that one open source, one closed source that would solve the same problem. Turns out that not only do these programs make the same mistakes, it also turns out that the bugs tend to accumulate in the same places. And that's for two totally different code bases, where two development teams, one open source, one closed source, simply have implemented a specification, and they made the same mistakes, which was somewhat depressing if you believe in closed source or if you believe in open source, whatever you take. Yes. Yeah, the question is whether we ever consider the age of the bugs. If something has been fixed a long time ago, and if something has been fixed a long time ago, or if stuff is all new. Yes, this is actually something we're looking into. We're looking into whether a fix disrupts the stability of a particular component. The idea being, if you made and this is something that you can find confirmed in quite a number of studies. If you have a piece of software and there's lots of change being made in the last couple of weeks, this is much more likely to have bugs than something which has been stable for a long period. And therefore, it's not so much the age of the bugs that count, but rather the age of the last change that counts in this place. And this again is, of course, an indication of the testing process, which is not yet perfectly aligned with the number of changes and the risk they induce. Yes. So the question is, can't we solve this? Can't we solve this problem at its root cause? And the question is, from all we learned about old code bases, what can we do better about new code bases in the future? That's a tough question. I believe that new systems will have bugs just as old systems will have bugs, simply because eventually they are made by humans and human specifications are incomplete. And there's always a risk of people introducing bugs. But what I see, for instance, what I see in automated debugging as well as in manual debugging is that there's quite a number of established techniques which help you tremendously during debugging. And these techniques also make your program much more stable, and also help you as a human to understand better what you're actually dealing with. One such feature which is totally underestimated in my opinion, is contract assertions. If you, as a developer, write down, this is what I assume about the parameters of this method, and this is what I guarantee to come out in the end, this serves three purposes at once. A, it helps you documenting what you actually think about, and therefore also your colleagues. Second, it gives you an automated test, fully automated test, while your program is executing all the time, and you do have these extra CPU cycles for that. And third thing, if you do debugging, if you have a program that's full of assertions, full of contracts, if you do debugging, you know, well, these are the assumptions. You have all these inline checks which you run all the time while your program is executing. Debugging becomes so much easier because the very moment the state becomes faulty, chances are very high that some contract will catch that, and manual debugging as well as automated debugging, will catch the bug much faster and solve you lots and lots of problems. And this is probably the one single recommendation in terms of debugging and analysis I would give to new programs. Yes. So the question is, to put it very generally, what's the best way of using assertions? Or isn't there also a risk of me making bad assertions rather than good assertions at this point? And the question also is, rather than having assertions in my code, should I better come up with something that's outside of my code, say some formal external document? I think that it's very important to have assertions right within your code. I also think it's important, for having for learning and for teaching how to use them as part of your daily programming work. But such assertions also can form a nice base for formal verification, for symbolic techniques. This, of course, requires that you have a language for assertions that is expressive enough to express what you want to say, and on the other hand, it's still limited enough such that you can actually reason about it symbolically. And there's also, and in this area, there's also lots and lots of things to be done. But we see, in particular in companies like Microsoft, Microsoft is definitely a place where if you want to look for bugs, yes, it's a great place. It's a great place to search for. Where the research department of Microsoft does large efforts in teaching programmers first to write specifications, to write contracts, which are first checked at runtime, and then the whole thing is being extended over time in order to form the base for full-fledged formal verification. And I think that having such an incremental approach that caters to developers just as well and at the same time increases quality is a good way to go. So I'd like to take this moment to close officially the talk. Thank you, Andreas, again. So for those people who need to run, you're officially free to go now. If there are any more questions, we still have time. I'm sure you'll be happy to answer. We are also maybe a discussion or coffee, something like that. We'd like to ask some questions. Thank you.